Hello, Ivy.
Hello,
How are you?
I'm doing well. How are you?
I'm good. I'm good. Sort of trying to polish up my fluorescence knowledge, realizing it's pretty fuzzy.
Honestly, it's pretty fuzzy for me too.
Well, there we go. Good. We can polish together.
Life is all about learning and relearning.
Oh my gosh, isn't it? Oh, my goodness. Let me see if I can turn on my camera here. Here we go. Start video. There we go. Yep, that's me.
Hey, Dr.
All
T.
right. Hey, Calvin. How's it going, buddy?
Hey, good, Dr. T. I thought you were in lab today because you said like you're like fixing your fluorescence. I thought you were fixing like
Oh, yeah. No, I didn't come in today. Uh, Yesterday threw me off because yesterday it was too smoggy and they closed the building.
um,
And then I don't know if did they open it today?
yeah, they email on I don't think so, but they emailed us for tomorrow that it's open. So
Oh, okay, cool. It's just if it's not one thing, it's another.
Mhm.
You know.
Dr. T, I have a question.
Yes, sir.
For the paper, are there there's like 3 papers in the PDF file, right? That's my you
Right,
posted.
right. And more are coming, but I don't want you to just read all of them. We're gonna
Sure.
sort of step through them a little bit carefully because I don't, it's not all for our consumption. We got to be judicious. Otherwise,
Okay,
it's
because I
going
was
to be overwhelming. Yeah.
oh yeah, because I was about to say like this paper is really overwhelming.
Yeah. 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 It is. It is. But we'll get through the meat of it. We'll get through the important bits.
Yeah,
Hold
no,
on, just a sec. I'm gonna close my window here. Okay. So, all right. So let's see. Also got to share my screen here. Uh, so, what do you guys see right now? You have my picture, right? But can you see my screen?
No. Oh, we see your face.
see your face.
Sorry about that. Okay,
That's
hold on. Hold on. Okay, hold on here. Let's see here. Share your screen. There's normally something that says, share screen. There we go. And I'm going to share it by screen here because that is the smart way to do it. That way you can switch things around and you don't get confused. So you should see now like maybe a thumbnail of my face, but then also a Word document. Is that what you see?
Yeah.
Okay.
Yeah, pretty much.
Excellent, Kai. So good to hear your voice. I miss you, Kai. Oh, I gotta get.
Huh?
Yeah, if you wanna, I gotta get some 298 things out there. If y'all wanna join up.
Oh, okay.
Yeah.
Yes, I need an ad code.
Yeah. You need point missions. Okay, so let us see here. So I wrote some stuff down. This is just sort of a review of what I blathered on about in the first day. Sort of this idea that there's a minimum light quantum, a minimum size excitation in the electromagnetic field, and that the there's a matching condition between a photon and an electronic state. And it's funny because the same proportionality, H, comes up for vibrations and other things like that. And I just kind of wanted to formalize that here just a little bit here, you know. There's a vibrational quantum number V, and you add a half to it. The V starts at 0 and goes positive. And you add a half to it, then multiply by root K over mu times H bar, and that'll give you the energy spacings for a harmonic oscillator. So when you get the selection rule for transitions is delta V equals plus or minus 1. So you'll get these steps that are basically H bar K over mu, H bar root K over mu in magnitude. But in the PChem lab manual, it's called omega E and whatnot. But you use it to calculate things like K. So it's just a funny coincidence, you know, and I'm told that it relates back to relativity, why there's this, why H bar shows up in all these funny places. But let's see here. Oh, and I couldn't resist. I calculated the density of the proton, and it's 670 trillion grams per cubic centimeter. Million? No, 1,000, million, billion, trillion. Yes, 670 trillion. So the next thing I wanted to emphasize was that the world is, you know, the scientific world is made of models, right? And we're always trying to get better models. And sometimes, you know, we hit a point where we don't have enough data and things can get a little bit off the rails. And that's basically where things are now. They've been at a very satisfying point from the cosmological and the quantum realm for a long time, but they can't be put together somehow. So speaking just on the quantum level, though, the differential equations we have are spectacular, and they work amazingly well. And when you add corrections into them for really weird stuff, like virtual particles, you actually need them. And you can look up the Lamb shift, L-A-M-B, the Lamb shift, and you can see how the spectrum of hydrogen needed corrections. And the corrections turned out to be dielectric corrections for virtual particles, strangely enough. But the exact wave functions, SPD and F, and sigma, pi, and delta for molecular orbitals are, again, amazingly good. But in order to apply them to real atoms and molecules, so things like a hydrogen atom, for example, has 2 nuclei and they vibrate. And you have to use an approximation that the nuclei are stationary to solve the electronic problem. And then you have to ignore the electronic problem and treat the restorative forces like some sort of anharmonic spring to solve the vibrational problem. You know, then you have to consider it rigid to solve the rotational problem. So you have to kind of do this piecemeal, right? And to some degree, that's completely justified, but in other ways, it's a little bit odd, right? So that being said, once you take these orbitals and you use what's called the variational principle, that when you apply the proper quantum wave functions to an atom, molecule, or ion or whatever, then you'll get the lowest energy out, right? That's an important that's one of the guiding principles in all the quantum chem, is that basically you can use the H psi equals E psi sort of formalism to get the energies out of each different state, and then the psi function is you're going to have to put in an S, a P, a D, or an F, or a sigma, pi, or a delta, or whatever. And then in order to, and then using some tricks, you can a lot of times get the energy out. And then if you've used the proper wave function, then you'll get a minimum energy. And there's all kinds of tricks to be played around that. Very few of them I actually know, but I know enough to be dangerous here, which is that to know that these are approximations, right? They're models of reality. So, so that is my spiel, where I'm sort of telling you what I know, right? And the idea is that in some ways we're spectacularly good predictors, and in some ways we're incredibly primitive in what we actually know, and the getting mathematics to actually play ball with us. So now onto real systems, fluorescent systems to be exact. We talked a little bit last time about how any absorption or emission or fluorescent spectrum that you record or see will be will be an ensemble average over time and solvation, and many different molecules, right? So billions upon billions of molecules average over millions upon millions of tumbling timescales, solvation timescales, and all these perturb the energy states of the molecules a little bit, right? So every time, if you take if you took an HCl molecule in the gas phase, for example, and a water molecule in the gas phase, and you allowed them to bind, right? Probably the hydrogen end would bind to the oxygen, right? That would actually lower the electronic and vibrational energy levels of the HCl molecule and of the water molecule, right? So if you're doing spectroscopy on a solvated molecule, you can look for, you can generally assume that all of these energy levels are being lowered by the solvent interactions, unless they're not, right? There can be transient disfavorable orientations that raise the energy levels as well. Does that make sense? Yeah. Does that make sense? No, no. Oh my God. Okay, so it will. It'll make sense. It'll make sense. So, so let's think about. Here's a good Jablonski diagram. This is getting a little bit more real here. But the the idea that we don't see lines, in real in solvated systems, right? In the gas phase, we see lines because all the molecules are identical. But in the condensed phase, we generally see ensemble averages, right? So let's take a look at this Jablonski diagram of a molecule with three, let's say, singlet energy states. So first of all, what do I mean by singlet? Who knows what I mean by singlet or triplet energy states here? Okay, so truth be told, I don't know that much about the multiplicities, but I have an idea. So I can turn light on. So I'll use a different piece of paper here. But a singlet state basically has all paired electrons. And then a triplet has two parallel spins. So now all paired, all anti-parallel. Right. Oops. Then a triplet has two parallel spins. So triplets are paramagnetic. And singlets are diamagnetic. And so most organic molecules with like closed Lewis structures, with Lewis structures that don't have radicals, that all form bonds. You know, there's an even number of electrons, etc. These are singlet states, right? And I kind of forgot what I was going to say about singlets, because I know you guys are listening, but I feel so disengaged. How can I be more engaged? I think I need someone to say something.
Hi, Dr. Terrell. How are you doing?
Oh, Calvin.
I'm good. I'm good, Kenya. Thank you. I'm much better.
You were gonna call me
Much.
Catherine, huh?
No.
Yes, you
No. I'm not going to mistake you with anyone.
Okay.
You are Kenya. You are and always will be Kenya.
This is true.
Okay.
Something.
Dr. Terrell,
Yes.
okay. Are you gonna be posting the notes and the recordings on Canvas?
Yes.
Okay.
I think I got this recording posted onto Canvas, but I can't remember exactly where. I'm in this weird state in terms of like learning how to use Canvas, and there's this thing you can add modules and like, but how to add content to module, I don't know, and it's like weird, and that's how you organize them, and so confusing. But anyway, so now, so the singlet triplet thing, let's talk a little bit more about that. So if you have just two states here, right? You've got a singlet ground state. You've got a singlet excited state, S0 and maybe S1. And then you can also, a lot of times, generate a triplet state from this. Right, and I'm not exactly sure whether this is a different molecular orbital or simply, oh, I'm sorry, I did that wrong. T1 is going to be anti-parallel here. I'll deny that I ever did that. So there's a T1, right? And I'm not exactly sure whether these are the same electronic state or not, or if there's any requirement. But and triplets are not always lower energy than the corresponding singlets, but they often are. And I think that's probably partly a consequence of the fact that they're not very readily observed unless they are lower energy. Because what happens is that there's these processes happen by the absorption of a photon, and then by this is called intersystem crossing. Right, where the singlet turns into a triplet. And the thing, the intersystem crossing is normally a little bit slow, right? It's slowish, right? Microseconds to seconds, right? And so oddly enough, that also makes their relaxation slow. So this is called phosphorescence. And that's also slow. So you guys know about glow in the dark stuff, right? So, okay, Calvin knows about it, but I don't think that Carla has ever seen a glow in the dark thing. Is that true, Carla?
I definitely have.
You have?
We use them.
Oh, you use them in Chem 1A?
When we teach sometimes, yeah.
Excellent, excellent. Okay, cool. So, the triplet states, you populate them by irradiating the bejesus out of the thing that's gonna glow later, right? Kenya, do you get more photons out than you put in phosphorescence?
No.
Exactly right. You almost never get more photons out than you put in. And if you have like glow in the dark stars or something, they're going to glow like for an hour at night. How long does it take to fully charge them up with light? Adam, you know the answer? I gave it away in the question. Hours. Right?
There's a long time.
Yeah, it takes a long time. So the problem is that if the relaxation is slow, then the absorption is low probability also. So you got to use a bright light in a long time, and then slowly it'll start to relax, right? The faster the relaxation, the brighter they'll be, right? But the shorter that brightness will be there for, right? So that's a trade-off with these types of things, right?
So I have a question.
Yes.
For the triplet state, is the reason why it emits so slowly is because they have the same spin orientation?
Right. Yeah, so there's no way for me to not bullshit when I talk about this, right? But if you accept a little bit of BS, then the problem is that the transition moment integral is zero, right? If you take the psi star, and then it's a dipole moment operator, and then psi, and I don't know what the hell you do with that. You integrate this thing, and if you've got a triplet and a singlet, it comes out to zero, right? Which means an infinite lifetime. Means that there's never a transition available. So you need to use the magnetic part of the spin orbits in order to get this to be non-zero. And it's just much smaller than the electronic one if you've got singlets and singlets, right? Singlet and singlet, it's It's much greater than 0. So that
Can
was
I ask
like,
a quick question? Sorry.
yeah, of course.
Could you remind me the difference between the diamagnetic and paramagnetic again?
Oh yeah. So diamagnets are weakly repelled by magnetic fields, right? I was raised on the idea that diamagnets did not interact with magnetic fields, but in fact, they're weakly repelled. And paramagnets are relatively very strongly attracted to magnetic fields. So we're all familiar with ferromagnets, right? Which is iron that has a permanent magnetic moment, right? And that's where the paramagnetic states are locked in crystallographically. And it's a combination of crystallography and sort of coordination chemistry stuff in the iron, in the electronic states of the iron atoms in an iron crystal, right? But but paramagnetic things will simply respond to a magnetic field while the magnetic field is applied, and then when the magnetic fields will go, they demagnetize instantly. Does that make sense? And it's a phenomenological description, right? There's not more that I know to that description.
Got it. Thank you.
You're welcome. So okay, so let's talk a little bit more then about. Yeah, so let's talk about. You can see the Word document with the Jablonski diagram now, right? Good, excellent. So now there's this goes left to right, A, B, and C, right? And you notice on the A, there's upward pointing arrows, right? And these upward pointing arrows all start at E0, right? Capital E0 and little e0, right? And my question is why? So this is the description of observed phenomena in molecules, right? And an upward pointing arrow corresponds to what type of transition? Or it's an excitation, but what is involved in that excitation? What two particles? One of them is a molecule, the other one is a blank on. Calvin? What is the other particle? It's called a blank on.
He typed it.
Darn this. It's Alt H, right? So I can see it. No, I need to see. Zoom, Alt H or something. How do I get the chat?
He said photon.
He said photon.
I know, but I want the chat. Because
I think you hover over either the top of your screen or the bottom of your screen and screen share.
okay.
And then
Screen
there
share.
should be a
There it is. There
Yeah.
it is. Participants. No, I don't see anything.
It's not
Maybe,
right.
there's more here. Okay. Okay. Breakout rooms, pause, stop, closed caption. Darn it. Let's see here now. Okay, so I got participants. Now I'm going to do Alt H. Ah, here it is. Okay, good. I keep freezing. Oh my gosh, I'm sorry. It's not me. I do not know what it is. I've got the most expensive internet you can possibly imagine, and I do not know why. Am I freezing for everybody?
Not for me.
Okay, good. So it's your fault, not my fault. Okay, so so you guys see this Jablonski, right? So the arrows start at the bottom because Adam.
I mean, I know it's its lowest energy state.
Yes.
I just don't know why.
Okay. Why? Okay. So let's do a thought experiment. Pauline has a bottle full of molecules. Is that right, Pauline? You better
No.
answer. You better answer. You don't? Okay. Good. So you don't have a bottle. Ah. Okay. Kenya is now going private. Okay. Oh no, that's two. So yeah. So it's a ground state, and in Pauline's bottle of molecules,
It doesn't exist.
it exists in my mind. And how many of those molecules, Justin, are in the ground vibrational state and the ground electronic state? She has 100 molecules. How many? Justin. Oh, Justin's asleep. Justin's not here. Okay, Leslie. Leslie's not here either. Aditya, you're here. You
Would
were
it be
here.
terrible to hazard a guess?
No, it would never be terrible to hazard a guess. Please hazard a
Justin
guess.
wrote a message in chat.
Oh, Justin wrote a message in chat. Oh yes, I'm not sure, but maybe half. Okay, that's a possibility. That's a possibility. It's completely wrong. Actually, half is the if there's only two states and it's an infinite temperature, then half is correct. But we're talking room temperature, which compared to infinite temperature is A, cold, or B, hot. Boltzmann distribution. Yes. So all states is not correct. Boltzmann distribution is a distribution, yes, but it doesn't answer the question. And then Ivy says most of them. Ivy so far is the most correct because she said most. And in fact, KT is about 60 millivolts to go back to the Boltzmann distribution. Therefore, and I think 60 millivolts is several thousand wave numbers, like 3,000 or 4,000 wave numbers. Therefore, most molecules are in little e0, big E0 at any given point in time at room temperature. Does that make sense? It's just the way things work. I didn't make it up. Just the way it is, right? Okay, good. Most of them is correct. So why do the arrows, the upward pointing arrows, start at big E0, little E0, Kevin? Kevin. Kevin.
What was the question?
Why do molecules start in big E0, little E0? Why are the arrows going up? You must answer, I don't care how wild your guess is. And it must be out loud, not in chat, because I don't know what's coming up on chat. I've got 17 things to look at. Okay, who?
Energy levels?
Okay, that is not the answer to why.
Okay.
Oh, now he thinks he's off the hook. He remuted himself. Oh my God, Kevin, you are not off the. Kenya, do you know the answer?
Did you say why are they starting off at the first energy level?
Yeah. When they go
Because
up.
it's the first energy level.
Okay, well that's
You
good.
can't-
That's good.
Like you can't start off at like energy 4. You have to move up, right? Does it have to do with like emission and absorbance?
Yeah. You actually have a very good working understanding of this, right? But there is a little tiny bit deeper cut as to why. Why? I mean, because what we observe when we do absorbance spectroscopy is these arrows and these arrows only. We don't see E1 to E2, and we don't see, E2 to E4 when we do infrared. We only see these transitions that start from big E0 to little E0 and little E0, right?
Does it have
You start at 0? Is that what you mean?
Does it have to do with
Yeah.
orbitals? Like the
It's more basic than it's simpler than that.
Is
Calvin,
it,
It takes more energy for electrons to go from their ground state to an excited vibrational or electronic state.
Yeah, true.
Temperature.
More energy than what, though?
More energy.
Yeah. So, Calvin, do you know the answer? Because I can see you're doing something there.
He said absolute 0 internal energy.
Oh, okay. Okay, well, yeah, but we're not at absolute 0. We're at room temperature. When we do these experiments at room temperature, and all we ever observe is these little arrows here where it says IR. This is what we observe when we do an infrared spectroscopy experiment. And then these larger arrows are what we see when we do, say, a visible or an ultraviolet absorption experiment. And these are not too far. They may be a little bit short from here to here. But
is it
yes.
is it because the little E1 and the vibrational states happen so quickly to the point where we don't see them?
I love it.
You said it was only observed. That's the only thing we observe is the
Right.
big arrow.
Right. So yeah, we do observe little E0 to little E1. That upward going arrow, we observe it because when we irradiate this thing with photons equal to little E1 here, or little E1 minus little E0, right? Then we see a peak. And when we irradiate it with photons equal to little E2 minus little E0, we see a peak, right? But we don't see a peak when we go from little E4 to little E3. We just don't see that. If everything was hanging out here in E3, and we could draw an upward arrow between here and here, then we would see that, but we don't see that. Does that make sense?
Oh, does this have to do with the quantum numbers changing and stuff?
Yeah, but it's much more basic than that. It's basically everything. Like you guys already answered it, right? What fraction of 100 molecules is in this state here, big E0, little E0? Like 99% at room temperature. Right, that's what the Boltzmann distribution says. That's why Boltzmann was all excited, and that's why he eventually killed himself, because nobody else got excited. and they told him he was crazy, right? So he got so depressed. Yes, right, Dan? He got so depressed he killed himself.
I definitely know that as only a word that I've heard in PChem or something. I don't really know the meaning. I have a guess though.
Yes.
I'm a little confused, but is it because like the excited states like E1 and E2 have virtually no population?
Exactly.
So okay.
Exactly. Yeah. So when the photon comes along, it's got to interact with molecules. Oh, Carla wrote 0, 0, 0, and then a whole bunch more zeros.
Sorry, my notebook was on my keyboard and I didn't realize.
Oh, that's
I'm sorry.
that's a very profound message. I like it. I'm gonna analyze it.
I thought she was saying like, oh.
Oh.
So sorry.
Okay, so if you're a photon and you're singing, you're going through this liquid, right? You're not going to hit any of these other states because they're not there. I mean, there might be 1 in a billion or something, and fewer as you go to higher energy. But the ones that you do interact with are these ground states. Does that make sense? Somebody say yes, for God's sake, please.
Photons
Yes.
interact with ground state.
Yes, exactly, because there just are more ground states in there. Right? So now, when arrows go up, that corresponds to absorption of a photon. Right? That's just the shorthand in this diagram, right? So the photon disappears and the state changes. And so if we were to make a little spectrum out of this part of the Jablonski diagram, let's see what that would look like. Okay. Actually, I'll get a third piece of paper. Okay. So what that would look like is something like this. We have energy increasing this way, right? Well, what if I said also that we had frequency nu bar in wave numbers increasing that way? So it just so happens that E equals h nu is equal to hc over lambda is equal to h nu bar, something like that, right? Times some constant. So nu bar here is directly proportional to energy. Right? So if we were to say, we can start this guy maybe at, say, some very low energy, say 200 wave numbers, right? And we can scan that energy up. And then, the photons of this energy are going to come in, and they're going to see all these states. But they're not, these photons here don't have enough energy to promote this state, right? When they get to this energy, then they do. So what happens is in the spectrum, we see a peak there, right? And then when the energies equal this guy, we see a peak there, and that's for this first transition, the second transition, etc., right? You see a peak there and a peak there, right? Does that make sense? This is just an absorption spectrum on its side, starting at a low wave number because we can't start at 0. We have no detector for 0, and this guy may be 3,000 wave numbers, which is the practical upper limit for vibration of molecules. And And this just corresponds to the different energy spacings available in that molecule. Right? So, does that make sense to everybody?
I have a question.
Yes.
The intensities, they should be different, right? They it like depends on something else.
Yeah.
It's
So
like,
Mhm.
sorry, it's like how like forbidden, or it's something about that, right? Or
Yes.
is that different?
Yeah. Yeah. Exactly. There's the first cut at that is the transition dipole moment integral, and
Oh, I see.
basically it's the uh, the dipole moment of the ground versus the excited state. You integrate that over, whatever vibrational space you're going through there, and that tells you what the amplitude of the vibration will be, relative to other things. And and it's easy for it to come out to zero. And generally, what people look for is they look for the symmetry of the two states. So, for example, the zero state looks like that, and then there's another state that looks like that, right? Then there's a state that looks like that. So this is E equals 0, E equals 1, E equals 2, right? And it just so happens that when you integrate 0 to 1, the dipole moment integral is non-zero. How do you say, not equal to 0, right? When you integrate 0 to 2, the dipole moment integral is 0. It has to do with the symmetries of these states. I forget, there's a really cool little argument about that. I'm so sorry. It's shaking. That probably makes it super fuzzy for y'all, right?
No, it seems pretty clear.
Okay. Okay, good. Thank you. So the intensities have to do with the magnitudes of those integrals, and this is just a harmonic oscillator series, but there's a lot of subtlety there I have no idea about. So but
Thanks.
yes, go ahead.
Oh, just thanks.
Oh, you're welcome. And so now so this is sort of like, now here is a huge problem for you all. What if a photon interacted with this state and it went up there, right? Where would you see that energy on this axis? Where would that show up?
Would it be indivisible?
Good guess. Incorrect. Good guess. Incorrect.
Would you see it on like the lower end because it's a smaller like energy difference?
Yes. Yes, you would. Yes, Carla. Yes. So you would take this energy and you would simply translate it down here, right? You would say, okay, it's equal to this height, right? And so that peak would show up, maybe they're all too damn evenly spaced, right? But it would show up here, because it's just a small energy difference. Does that make sense? So when you put things on the side, it's great for starting at E0, E0, right? Because the photon energies on and the light energies line up. And the, photon energies and the molecular energies line up. But otherwise, they don't line up. Okay, so moving on forward here. Let's see. Okay, so we're going to go back to the Jablonski diagram. So we know that for this region here, we will see the infrared absorption spectrum, right, of the molecule. Yes? So in this case, what would we see for the visible light absorption spectrum? How would this molecule here, when interrogated with visible light, what would that spectrum look like? If you had this molecule, say, floating around in some water in a UV vis, and you did a scan from 800 nanometers to 300 nanometers, and you looked at the entire visible, plus a little bit of the UV and the near IR, you looked at the spectrum of this molecule, right? What would that look like? And it's just going to have peaks, right? How many peaks is it going to have, Adam?
It should have two main peaks, and then
Yes. Actually,
would you see the vibrational energy changes when it reaches?
If you have it in, if it dissolves in something like a perfluorooctane or something very nonpolar and very nonpolarizable, then you can see the vibrational parts. Even there's probably other examples of solvents that solvate extremely poorly and they don't perturb the levels very much, then they're not broadened into a continuum.
Okay.
But if it's in water, then they're broadened into a continuum, right? So this guy here, this is going to look like, let me go back to here, and we'll go. Right. And so now, and say these are all singlets and there's good transition probabilities between them all, right? Then if we have a UV vis spectrometer, we're going to start this around 800 nanometers, right? So lambda in nanometers is equal to 10 to the 7th over nu bar in wave numbers, right? So nu bar in wave numbers is equal to 10 to the 7th over lambda in nanometers. And if it's let's say it's 1,000 nanometers, so 10 to the 7th over 10 to the 4th nanometers. And this is going to be nanometers per centimeter. This is going to be equal to 10 to the 3 wave numbers, which is equal to oops, not 10 to the 4th nanometers here, 10 to the 3rd nanometers, because that's going to be 1,000 nanometers. That's the sort of the edge of the operational UV vises. That'll be 10 to the 4th wave numbers. Will be 10,000 wave numbers. 10,000 wave numbers is above the operating range of most FTIRs, right? So 10,000 wave numbers is 1,000 nanometers here. So 1,000 nanometers is going to be where on this diagram? Where what might we be starting at 10,000 wave numbers or 1,000 nanometers? Would it be here? Maybe around here? Would it be here, or would it be here, or would it be here? A, B, C, or D? Everybody vote. A, B, C, or D. Use the chat and vote if you can. D, 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 A. Okay. B, and a bunch more D's. Okay. Excellent. So, that's really interesting. Okay. So, the long, so 1,000 nanometers, is that the long wavelength end of EV-vis or the short wavelength end? Dan, just say it out loud. Shout it out.
Short?
No, long wavelength end.
Okay.
You knew that, right, Pauline? Yes? Say yes.
Yes.
Good. See, Pauline knew. Kenya knew too, right? Because she took 155. Yes, she nodded. Okay. So, so 1,000 nanometers is the long wavelength end of a UV-vis, right? There's normally not much happening around 1,000 nanometers, except for there's an overtone for water stretching vibrations, but it's pretty weak, right? So now that is going to start around point. Aditya got it. Point B. You are the go-to guy, Aditya. Oh, wait, and also Adam. And that's it. Okay, just Adam and Aditya. Okay, and then Calvin said long. Does that mean that it feels like time has stopped because I'm taking so long to make points?
I think he
Long
was
wavelength.
asking,
Oh, long wavelength. Yes. Okay, good. Okay, so now it's going to start around B, right? So the spectrum will start around 1,000 nanometers, and let's go to 200 nanometers. And so it'll be up here, right? So the spectrum is going to go long and then long like that, right? Does that make sense? Because we're not at a low enough energy to go through these guys directly, but we will go through these peaks, right? And there'll be a most probable transition and a most probable transition, etc. That's all the weird stuff that we never get into as not hardcore physical chemists. So, so going back to the Jablonski diagram here, we'd see these transitions through these visible manifolds here, right? Now, if we wanted to observe the fluorescence from state 2, let's say we wanted to observe this fluorescence here from state 2. This long, this long arrow going down here from state 2. What wavelength should we pump into this molecule? Short or long wavelength?
short.
Exactly. Which means the arrow will be short or long? The up arrow is going to start here, and it's going to be short or long.
Long?
Long.
Exactly. Good. So we're going to pump into E2, right? And let's say we use, say, 200 nanometers, which corresponds to E0, E0 to E2, E double prime 4, right? So we're gonna pump energy in at this wavelength, right? Now we're looking for fluorescence from this molecule, right? So we're not going to monitor at that wavelength. We're going to monitor at longer wavelengths. And what's the first thing that's going to happen to this molecule? After this state E double prime 4 is created, there's some very short, that's a very short lifetime state because of non-radiative relaxation. Oops, non-radiative relaxation, right? So it's going to go bonk, 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 bonk. And then it's going to sit here at E2, right? Now, E2 has two choices, non-radiative and radiative relaxation, right? Yeah? Does that make sense? So the non-radiative pathway here will go down and, it could go down to here and then we could see this fluorescence, yeah? But we never see fluorescence from these upper vibrational states. Question for anybody: why don't we see fluorescence from these upper vibrational states? This guy, neither E double prime 1, 2, 3, or 4, or E prime 1, 2, 3, or 4.
Is it too fast?
Something's fast, yes. What is it that's too fast?
The relaxation?
Yes, exactly. And what type of relaxation is too fast? Electronic or vibrational?
Vibrational?
Exactly right. Good. So the vibrational relaxation is so fast, then it's a non-radiative relaxation is so fast that we never see evidence of these states from fluorescence down like that, right? You know, there could be a decent probability, the lifetimes of these states are so short that what happens is that as we pump in here, we literally accumulate, after we turn the light on, we will accumulate this state here for a certain period of time until the rate of creation equals the rate of decay of this state. And the rate of decay of state E2 is equal to the sum of the processes, the radiative and the non-radiative processes for the relaxation of that state. Does that make sense, Dan? Excellent. I got a thumbs up there. Cool. So now for state E2 here, then, if we pump with energy equal to E double prime 4 minus E0, right? This high energy. We will observe fluorescence from state E2 to E0, right? What other emissions might we observe? Carla? What think you? So when I say we're going to observe emission from excited state E2 to E0, that means that we'll see a peak at a fairly high energy. It's up here, right? We'll also see a peak at a much lower energy down here, E1, right? If there's substantial amounts of transfer from E2 to E1. Does that make sense?
Can you say that again?
Okay. So if we pump in energy up here, we see fast relaxational, vibrational relaxation to state E2. Then we will observe from E2, we will see peaks corresponding to the relaxation from E2 or E double prime 0 down to E4, E3, E2, E1, E0, right? Does that make sense? Kenya gave me a thumbs up. I love it. I don't know how to do that, but it's kind of cool. So also, if there is, say, for example, you go this non-radiative route here, then you've got state E1, which can then radiate down here. Right? So you should see a peak, a fluorescence peak, oh, I'm sorry, fluorescence peak up here, a fluorescence peak up here. Does that make sense? Okay, so now I'm going to use someone's handiwork from Chem 155. We're going to illustrate this using rhodamine 6G. Okay. So here is the absorption spectrum, the emission spectrum, and the excitation spectrum of rhodamine 6G. This is a 1 micromolar solution in water. Okay. And now, first of all, let's look at the absorption spectrum, the gray spectrum right here. There's bumps all along this region here, going out to 400 nanometers, right? So these, and these are the 0 point for absorbance is right around here. This absorbance spectrum corresponds to the right-hand axis here. And there's absorbance going from 0.045 and then down, and then it peaks up here at about 0.085, and it comes back down to 0, right? So now there's probably more than one electronic state here, right? But in order to simplify this, let's just think about 2 states. One state that has a broad envelope of vibrations that are shorter in wavelength than 400, and then one that is centered around 530 nanometers. Okay? So there's some energy difference here, but let's just pretend that there's 2 different states here. Sort of a UV state and then a visible state. Right? And you can access all these states by absorption. Now, if you observe the emission of this molecule, and ideally, it would be better to probably excite around, say, 250 nanometers here, and then scan the. So if you put radiation in around 250 nanometers, and then you say, okay, what radiation is coming back out of this molecule? And what you'll see here is just this big blue peak. Right? You see a peak here because this is probably twice the wavelength of the incoming light, right? And then you see a bunch of light coming in at wavelengths redder at lower energies than that peak. And this peak mirrors the absorption peak. It's sort of like it's got a sharp rise and then a slope, and then the absorption peak has a sloping side and then a sharper cutoff here. So the blue and the gray have an interesting relationship that they appear. The main peak here appears sort of mirror imagey, one to the next. So so this is called the emission spectrum. You get the emission spectrum by irradiating the sample at a short wavelength, then focusing the light coming out of the sample here into a new monochromator and scanning that new monochromator to see what colors of light come out, right? And so this is sort of an orange yellowish emission. Right? So somebody explained to me then why we see this shape here when we scan the excitation, but look only at the emission around 600 nanometers. Why do we see the same peaks here and here and here? So let me try to get a couple things on screen here. Come on, you stupid thing. It's got to focus here. Okay, good. So, I don't understand the legend on this stupid camera here. Oh, there it goes. Ah, I have my light back. Yeah. So, we're going to assume this is, there's two excited states in this molecule, right? There's ground with its associated vibrations, and there's two excited states. Right? Now, the strongly emissive state here that shows up around, let me get rid of these guys just momentarily here. The strongly emissive state that corresponds to this peak or this one or whatever, comes from which of these two energy levels? E0, E1, or E2? So basically there's really only two states to consider. One coming from this mess down here, 350, 200 to 350, and then say 450 to 600 nanometers. And I'm asking, Kenya says E1. We have one vote for E1 here, being these peaks. Okay, so that's one vote. Adam also says E1. Let's everybody vote on this. Calvin, Dan, everybody, Carla. Okay, everybody's a little copycat. E1, 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 E1. Okay, so now I have license. Actually, although Justin didn't vote, neither did Leslie, because they're eating sandwiches somewhere else, I think, right?
Justin voted.
Oh, Justin voted? Oh, I didn't even see. Oh, there he voted. Okay, how about Leslie? Leslie vote? I think Leslie's having a sandwich. Yeah. There you go. Okay. Sorry for damaging your good name, Justin. So let's see here. So this at 500 nanometers, right? That does correspond roughly to this energy gap right around here. You know, something on the order of 500 nanometers, right? So to what wavelength would this energy gap here correspond? Oops, sorry. So if 500, E0 to E1 is around 500. E0 to E2 would be around what wavelength? You know, the way I've written this. You know, roughly. 250, exactly. 250 nanometers, brilliant. So emission, you know, but we don't necessarily observe these emissions, right? We don't observe those emissions. They basically don't appear, right? And not in this spectrum. Because the emission spectrum that we have over here, this blue line, is all flat over this area. You know? If we could put energy in here and see it coming out of E2, then we should see some structure here, but we don't, right? On the other hand, if we monitor the light coming out at 600 and we scan the wavelength going in, right? So this red spectrum here is all for light coming out around 600 nanometers, right? Yay, I love that it's red, right? So this is red light out when this wavelength goes in, right? That means that you're over in this area, and let's say you're pumping in 250 nanometer light. And what two photophysical processes at least are happening when you're exciting at 250 nanometers? Okay, let me start you off. There's an upward going arrow and there's a downward going arrow. where does the upward going arrow start? It's going to be over here. Is it going to start from here? Ha ha ha. E0. Exactly right. Pauline and Kenya, thank you. You started E0. And now if you're exciting at 250 nanometers, do you go into E1 or E2? E2. Excellent. Excellent, Adam. So we're going into E2, right? Then there's going to be some non-radiative decay. And then some more non-radiative decay. Then there's going to be fluorescence. Down here. Around 500 nanometers. That's why we see the big peak over here, right? The emission spectrum here, right? Now, my question for you guys for next time is why is the blue peak at 552, but the gray peak is at 528. And this is, gray peak is absorption and blue peak is emission. Okay, why is there that Stokes shift? Okay, I'll try and get that out on Canvas to you tonight or tomorrow. Okay, and then you can think.
Can you move the paper up?
Can I move the paper? Oh yes, thank you. Sorry. Yeah.
Thank you.
Of course, of course, of course. Okay, so I'm going to put a bunch of stuff onto Canvas for you, and keep looking at it. No assignments yet, except to look at the pictures in the paper. Just look at the pictures. That's all. See if they make any sense to you at all.
Just look at them.
Just look at the pictures, right? Maybe read the captions. See if the figure captions make any sense. Okay.
Okay.
Excellent. Good, good. I see you guys on Thursday, okay?
Quick question, Dr. Trill.
Yes.
On Canvas, it says the paper Smiles is due on August 27th. We can ignore that?
Yes, just ignore that. There's no points associated with it there yet. I didn't commit to the number of papers that we were going to look at. I didn't know it was going to take, I just have no idea how long any of this is ever going to take. So, and I enjoy when we take our time going through it, I kind of enjoy it. It's probably pretty boring. But that's why I'm a professor. Okay. See you guys next time.
Bye, Betsy.
Bye-bye.
Thank you.
Dr. Terrell.
Okay,
Bye,
we'll see you guys next
Night,
time.
Dr.
Bye-bye.
See.
Bye.